Welcome to this video lesson, which covers the full solution to the practice questions from lesson 18.2, which is the Cartesian form of the equation of the plane. In the first question here, we're asked to determine the Cartesian equation of a line that passes through the following points. Let's draw three not random, but in random locations, the points. We got A, B, and I give you some nice numbers here to work with. A little bit easier when we're calculating some of the values. So we got 3 points here. First, to find the Cartesian form, we need the normal to the plane. This plane over here, these are kind of it's moving in this direction, so the normal will be coming out of the page based on this drawing. In reality, it will look different if we plotted these points in 3 dimensions. But what we're going to do is we are going to use two vectors. Let's use A, B, and AC. Again, we can use different vectors. And to get the normal to the plane, we need to find the cross product between these. So first, let's find vector AB, and let's find vector AC. For AB, we are going to use the coordinates of B, 1, 1, 1, and subtract it by coordinates of A. That's negative 1, 1, and 1. Okay, now I chose the numbers so that we can get easy values here. We got 2, 0, and 0 for AB. And for AC, we're going to use two coordinates of C, which are 2, 1, 2, and subtract them by coordinates of A, which are negative 1, 1, and 1. When we subtract them, x will be 2 minus negative 1, that's positive 3. 1 minus 1, which is 0, 2 minus 1, which is 1. To find the normal here, the normal is going to be the cross product of vector AB and vector AC. So let's do that. We are going to have our vectors or unit vectors I, J, and K. And vector AB has components 2, 0, 0, and vector AC has components of 3, 0, and 1. Once we have this, we are going to get the positive I components by multiplying these two together and subtracting them by these two. So 0 times 1 is 0, and 0 times 0 is 0, so the first component here is going to equal to 0. For our negative j components, we are going to take 2 times 1 and subtract it by 3 times 0. So that's going to equal 2. 2 times 1 is 2 minus 3 times 0, which is 0. So that's 2 minus 0, 2 times negative j, which is negative 2. And for our positive z component here, we are going to use, let's use a different color, let's use purple. For the k component, we're going to block off the k column and multiply 2 times 0 and subtract it by 0 times 3. Well, that's nice because that's also going to equal to 0 minus 0, giving us this component as the z component as 0. Since this is a direction vector, we can also simplify this or change it to negative 2 times 0, 1, 0, and use this component here instead. This just simplifies our numbers a little bit. Okay, so here to get our Cartesian form of the equation, we know it's in form A, x plus b, y plus c, z is equal to d, or minus d is equal to 0. It doesn't really matter. I'll use this one for the purpose of this question. Our a value here is 0, so we get 0. Our x value, we're going to use one of the points that are on the line. Let's use point A. So that's going to be negative plus the b value, which is here, that's 1. times the y value of point A, which is 1. And I'll just write here, use A, which has coordinates -1, 1, so it's a little bit easier, plus our C component here, or our Z component here of our normal vector, so that's going to equal to 0 times the Z value here, which is 1, and that's going to equal to D. So I will have 0, 0 plus 1 plus 0 is equal to D, and therefore D is equal to 1. Well, our Cartesian form of the equation then will be ax plus by plus cz is equal to 1. My a value is 0. 0 times x is just 0. My b value is 1 times y, which is y. My c value is 0 times any z value is going to equal to 0, so y is equal to 1 is actually the Cartesian form of my plane here, and I am going to highlight this as my final answer. You may ask how this plane might actually look like, and I'm going to try my terrible artistic skills to try to demonstrate this. We got our x value, our y value, and the z value. These are the positive axes. And if the y value is always 1, that means that, let's say this is 1, and we're going to have a plane. If it was in 2 dimensions, it would look like a line like this. But when it's in 3 dimensions, it will be more like a plane in this direction. This plane always has a space 1 from the x-axis and 1 from the y-axis everywhere around. So at this point, it is 1 away from z. In this case, it's 1 away from x. And actually, let's try to see if we can put all our points here. So our first point here was -1 in the x direction, 1 in the y direction, and 1 in the z direction. So our first point is going to be somewhere here. That's going to be point A. Our second point here is 1, 1, 1. So that's 1 in this direction, 1 in this direction, 1 in the z direction. So that's somewhere here. That's our second point. And finally, our last one is 2, 1, 2. So that means 2 in the x direction, 1 in the y direction, and 2 in the z direction. So it lies somewhere on the plane in here. So if we expand the plane, because the plane goes infinitely long, we will find that as well. The second question tells us to determine the vector equation of the plane with Cartesian equation of 2x minus y plus 3z minus 24 is equal to 0. Well, when we do have the Cartesian form, we have the normal to the vector, so that's 2, -1, 3. But that doesn't really help us get the two vectors that are on our plane, or the two direction vectors of our plane. It does help us to find points on our plane. So we need to find a few points, well, at least 3 points on our plane, and once we have those 3 points, we can find the vector form. How do we find points on our plane? Well, that's actually quite easy. What we can do is we can let x and y equal to 0 and find the z value of the point that lies on that plane. So for point A, we are going to use x value of 0, 0, z, and we're going to plug that into our equation. So it's going to have 2 times 0 minus y, which is 0, plus 3 times z minus 24 is equal to 0. 2 times 0 is 0, 0. We're left with 3z is equal to 24, and therefore z is equal to 8. So point A, therefore, is 0, 0, 8. And this is the easiest way of finding the points, letting the other two variables equal to 0. You can also let things equal to 1 and find it, but why not find the easiest thing if it's possible? So for this one, I'm going to let 0, y, 0. And I'm going to plug it into our Cartesian form so that we get 2 times 0 minus y plus 3, our z value is 0, minus 24 is equal to 0, and we get negative y minus 24 is equal to 0, so negative y is equal to 24 by adding 24 to both sides, giving us y value is negative 24. And I'm going to plug that in here to get where my b value is 0, negative 24, and 0. For my point C, my third point, I am going to find my x value, I guess. Let's do that. So x, 0, 0. And I will have my equation as 2 times x minus y value, which is 0, plus 3 times my z value, which is 0, minus 24 is equal to 0. That if I rearrange this, I get 2x is equal to 24. And if I divide both sides by 2, I will get x is equal to 12, meaning that my point here is going to be 12, 0, 0. Now that I have my points, I can start finding my direction vectors. So I have 3 points, A, B, and C. So I'm going to find vector AB and AC. So AB is going to equal to the coordinates of point B, which are 0, negative 24, and 0. And I'm going to subtract them by coordinates of A, which are 0, 0, 8. And I will end up getting 0, negative 24, and negative 8. I can rewrite this as negative 8 times 0, 3, and 1. And since it's a direction vector, I can just use my simplified form here. For my direction vector AC, I'm going to take the coordinates of point C, which are 12, 0, 0, and I am going to subtract them by coordinates of point A, which are 0, 0, and 8, and I will end up getting 12, 0, and negative 8 as my 3 points. And this can be simplified as well. I can divide everything by 4, and I will get 3, 0, and negative 2. And again, since it's a direction vector, I can go ahead and just use this as my simplified form. Or again, it doesn't really matter. You can use this. You will also get the correct value, correct equation, because we are multiplying it by a parameter. And when we're multiplying it by a parameter, we can multiply it by 1 over 8, and then we will get 0, 3, 1. So to write our final equation in vector form, r is going to equal to a point. Let's use point A here, that's 0, 0, 8. The point cannot be simplified again because we're not multiplying this by a parameter. If we were, we could have changed this to 8 and 1 here, but that's not the case. This point needs to stay at 0, 0, 8. Whereas for our other ones, I'm going to use t, and I'm going to use vector AB, which is 0, 3, 1. And notice that if we were to use a t value of negative 8, we would get negative 8 times 0 is 0, negative 8 times 3 is negative 24, and negative 8 times 1 is negative 8. And that's why it doesn't really matter for direction vectors whether we're using the simplified form or the non-simplified form, because the parameter here can change this to either a simplified or a regular form. Finally, our last one is going to be another parameter multiplied by the other direction vector, which is 3, 0, and negative 2. And that is our final solution for this question. I hope that the first two videos were helpful in giving you an idea about how to change between Cartesian form of the equation and vector form, and how those two forms, what are the importance of those two forms of the equation of the plane. Also, I do suggest that you go to GeoGebra's 3D calculator and that you try to plot these maybe in Cartesian form and vector form and make sure that they're equal, and just to test it out and see what happens if you change your Cartesian equation. How does that change the normal? And how does it look like in 3D space? Because it is something that you haven't done yet, or you are not super familiar with, and it is important for you to practice the fundamentals so you'll get better at it. Thank you for watching.